Hello everyone, it is my pleasure to give this talk at Trends and Magnetism Conference. I will be talking about fast domain wall motion in chiral ferromagnets and ferrimagnetic insulators. This talk was inspired by potential applications of domain wall motion for creating new memory devices. And you can see it here. So here there is a schematic of proposal by Stuart Parkin and others. And basically the idea here that this blue and red domains are domains with different magnetization, and they're separated by domain walls. And basically if you apply current, we can move these different bits of information. And what you can immediately see here is that the faster we can move these domains, the faster, or the same way, the faster we can move these domain walls, the faster we can move information and exchange information. And that's why for this type of research, it is important to come up with materials where domain wall motion can be the fastest. And so that's basically the idea of this talk. And maybe just before starting to give you more details, let me remind you that there are many different types of domain walls and other spin textures, like the one shown here, this skirmion texture. And what was shown recently that in materials with perpendicular anisotropy and Zaleshinsky-Maury interaction, domain walls and as well as the skirmions, they move with higher velocities. So that's why in this talk, let me concentrate on systems with perpendicular anisotropy and Zaleshinsky-Maury interaction. And first of all, let me show you that in these systems, we can also get a so-called Walker solution. And also by solving this problem, well, I'll try to show you how we can maximize the velocities of domain walls. All right, so let me start. So let me talk about domain walls in nanostrips like shown here. And again, this nanostrip where we have perpendicular anisotropy, it actually means that in this left side here, magnetization will be pointing in negative z direction, and here where it's blue, it will be pointing in positive z direction. Also, well, I'll consider general problem when we have applied perpendicular magnetic field, and also we have applied in plane current. So you'll have both adiabatic and non-adiabatic spin transfer torques. And in general, this system can be described by Landau-Lipschitz-Wheeler equation, which is shown here. And so here, well, this equation is for evolution of magnetization M. And here the first term on the right-hand side, it represents effective magnetic field and basically precession of magnetization M around effective magnetic field. And this effective magnetic field basically given by a functional derivative of our micromagnetic energy, well, which is shown here. We consider all typical interactions here. So the first term here, that's exchange interaction. And then there are also two anisotropies. So this one is perpendicular or out of plane anisotropy. And next term is in plane anisotropy. Also, we have magnetic field, so the Zeeman term. And the last term here, that's interfacial Zaleshinsky-Maury interaction. So all these interactions, they can be represented in terms of dimensionless parameters like shown here. So that would be Kx and Kz would be dimensionless constants representing out of plane and in plane uniaxial anisotropies. This kappa would be proportional to Zaleshinsky-Moria interaction constant, D, and Hz, that will be dimensionless magnetic field. All right, so now, so basically the idea to solve this Landau-Lifshitz-Gilbert equation, and well, we can do it using this traveling wave ansatz like shown here. And if we use it and basically just plug it in Landau-Lifshitz-Gilbert equation, so we can find the following equations for domain wall profile in terms of spherical angles phi and theta. And so if we solve these equations, so then we can find domain wall profile. So first, let me start with a simple problem when we don't have Zaleshinsky-Moria interaction. So in the absence of Zaleshinsky-Moria interaction, I can just set angle phi equal phi naught, well, which is just some constant. And in this case, the system of equations simplifies. And so we can get the following system of Walker type equations in two-dimensional film. And actually, one can find analytical solution for the system of equation, and it will take the following form. So that would be a generalized Walker type solution for moving domain wall in 2 dimensions. Well, if now I can substitute the solution in the system of equation, then, well, from this last equation, I can find the velocity of the domain wall. And in general case, it will be given by this expression. And here the first term corresponds to velocity of domain wall driven by magnetic field, and the last term would correspond to current-driven motion. Also, well, here angle phi naught has to be found from this equation at the bottom. All right, so with non-zero Zaleshinsky-Moria interaction, well, we can also satisfy the above equations, but in this case, this normal vector of our domain wall profile should be given by the following expression, like the one shown here. So it's conveniently represented in terms of angle phi naught. And also we can show that in this case, this profile would be nail type. So this domain wall will be of nail type. And actually the exact analytical solution, this Walker solution, in case of non-zero Zaleshinsky-Moria interaction, will be given by the following expression. So here, well, in order to find magnetization, well, we need to know this normal vector n, and basically, well, we know it if you know what is angle phi naught, and this angle phi naught can be found from the following equation. So that's the general solution, but now, so let me look at some limiting cases. So there are two interesting cases. One of them when there is no current and there is only applied magnetic field. And then I'll consider a case of zero magnetic field and applied current. Okay, so let me start with the case of no current. In this case, actually the tilt angle phi naught can be easily found from this equation, and it will be given by this expression, which is rather simple result, and it looks like well-known Walker solution in one dimension without Zaleshinsky-Mori interaction. Okay, and also critical field for Walker breakdown is given by this expression, and that's again like rather similar to the case when there is no Zaleshinsky-Mori interaction. So basically, well, we see that this critical field is proportional to Gilbert damping alpha and proportional to in-plane anisotropy Kx. So we can see that in-plane anisotropy here plays an important role, because if it would be 0, it actually means that well, we cannot really sustain the solution in case of non-zero Zaleshinsky-Mori interaction, and because in this case, well, this critical field would be 0. Also, velocity in this case, in field-driven case, is given by this expression. So what you can see here, that when our magnetic field Hz is small, well, we can Taylor expand this expression, and basically we see that velocity will be linear in Hz. All right, so now let me switch gears and consider another interesting case. It's basically purely current-driven domain wall motion. So in this case, magnetic field is 0. And in this case, generalized Walker solution can be given by this expression. So here, well, first of all, we find critical current. So this basically the current above which we have Walker breakdown. And again, in this case, you can see that this critical current is given by ratio of anisotropies, and also given by difference between Gilbert damping and non-diabatic spin transfer torque beta. Also, tilt angle phi naught in this case can be found by this expression, and again, it depends on anisotropies and on current density, and also on alpha and beta. And so finally, the domain wall velocity is given by this expression. Let me just note that V here is normal velocity, so it's velocity in perpendicular direction to the domain wall. But generally, what is more useful is expression Vx is basically along the strip. And actually, what you can see that this expression is actually much simpler, and that's pretty much a familiar expression what you get, where velocity Vx is proportional to current along x direction, and also given by the ratio of fundamental constant beta and alpha. Again, beta here non-diabatic spin transfer torque, and alpha is Gilbert damping. Well, another interesting thing here is that well, we can solve well, this system of equations in general for like, any given current and magnetic field. And what is interesting that one can show that for certain ratio of magnetic field and current, domain wall actually will be moving with the profile being always perpendicular to x direction. So basically it means that this tilt angle phi naught well, will be 0. So like the one shown here in this picture. And what can be shown that in this case, velocity of domain wall is also maximal. And it's given by basically these dimensionless units, it will be just given by Jx. So it will be proportional to the current in x direction. And well, the ratio between current and magnetic field will be given by this expression. And if we use some typical parameters for these materials, so then we can find that actually velocity in this case will be roughly 500 meters per second, which is actually pretty high. And so that's pretty much shows that one probably should want to move domain walls with ratio of current density and magnetic field, like shown by this expression. And in this case, one can get the highest velocities. Okay, but so far the story was about ferromagnet with perpendicular anisotropy and interfacial Zelensky-Mori interaction. But what was shown recently that in ferrimagnets, one can get even higher velocities for domain wall motion. And in our recent work, we decided to look at it with my experimental colleagues. Actually, to look at ferrimagnetic insulator, this gadolinium iron oxide. And actually, because it's insulator, in order to drive this domain wall, it's better to look at bilayer with platinum. So in this case, if we apply current, the current will flow through the platinum. And in this case, at the interface, spin-orbit torque will be generated, which will be moving these domain walls in these materials. And actually, well, it was already shown that in metallic ferrimagnets, high velocities can be achieved. So what we try to see if in ferrimagnetic insulators, one can also get very high velocities. And so that's actually the case. And so first, let me discuss a little bit the theory. In this case, so if we use Landau-Richter-Gilbert equation for two sublattices, because in ferrimagnet we have now two sublattices, so we need to consider simultaneously dynamics of these two sublattices using Landau-Richter-Gilbert equation. And if you will do this, we will arrive at this expression for velocity. And what you can see here, that limiting factor here under the square root is, so basically if you can minimize expression under the square root, so then we can get the highest velocity. Okay, so the second term it's hard to minimize because, well, it's proportional to Zelensky-Mori interaction D and all these other fundamental constants. But actually this first term here, so we have here delta S, and this delta S is, it's a net spin density. So it's basically the difference between spin density on iron sublattice and spin density on gadolinium sublattice. And if we can change temperature in such a way that, well, this difference will be zero, actually we can cancel this first term. And so that's exactly what will give us the highest velocity. So basically, and actually, well, this delta is zero, corresponds to angular momentum compensation temperature, this TA, because basically when this net density is equal to zero, that means we have angular momentum compensation. But at the same time, it doesn't mean that overall magnetization is zero, because angular momentum compensation temperature generally does not coincide with magnetization compensation temperatures. And for this material, the difference is roughly 10 Kelvin. But anyway, so in the case when we have angular momentum compensation temperature, this expression can be rewritten in much simpler manner, like shown here. And you can see that velocity in this case will be proportional to the current density JE, and also it will be proportional to width of domain wall delta and spin hole angle theta, and it will be inversely proportional to the Gilbert damping alpha. So that's kind of very reasonable expression in this case. And so now let us see what happens in experiment. So if well, we can measure velocity dependence if we apply in plane magnetic field and current to this bilayer with this ferrimagnet. So we can see that at certain current densities, velocities can be very high. So they can reach more than 3 kilometers per second. And at the same time, the dependence on this in-plane transverse magnetic field, it's pretty much does not change velocity so much. Okay, so now the most important part here is shown in this plot to the right, and basically that's dependence of velocity as a function of temperature. And what you can see here that there are two temperatures here, Tm, which is magnetization compensation temperature, and Ta, this angular momentum compensation temperature. And well, they are not the same for this material, as I already mentioned. So Tm temperature is 220 Kelvin and Ta temperature is 230 Kelvin. And if you will look at velocity as a function of temperature, we see that the maximum is achieved at angular momentum compensation temperature, this Ta, exactly as predicted by well, this formula. And actually, the velocity is here very high. It's around 3,500 meters per second. So that's actually much higher than what you can get in ferromagnets with Zleshinsky-Maury interaction and perpendicular anisotropy. So that's why basically this experiment pretty much shows that ferrimagnets at angular momentum compensation temperature can be well, ideal systems for potential spintronic memory devices, because in this case, well, we can drive domain walls with extremely high temperatures. All right, so with this, let me start summarizing my talk. And first of all, I want to acknowledge all my collaborators. That's Val Slastikov and Jonathan Robbins from University of Bristol, Cyril Muratov from NJIT, Giovanni Finocchio from University of Messina, and a group of Wanzhong Zhang, who did all these nice experiments on ferrimagnets at Tsinghua University, and also theoretical support from Sikwon Kim for this theory on ferrimagnets. Also, I would like to acknowledge support from granting agencies, basically the one from UNSW, also Australian Research Council, and collaborative research project between UNSW and Tohoku universities. All right, so now, so let me just summarize this talk. So what I told you today that actually one can get exact analytical solution, which is very similar to what was proposed by Walker in one-dimensional systems without Zleshinsky-Maury interaction. But here we generalized this approach to two-dimensional films with Zleshinsky-Maury interaction and two anisotropies, perpendicular one and in plane one. And what we showed from these analytical solutions that by aiding in plane anisotropy, one can stabilize domain walls, and we show that they move with velocities in excess of 500 meters per second in case when the profile is perpendicular to the current. So basically there is no tilt of the domain wall. So that can be achieved by a certain particular ratio between a magnetic field and current. And also what I showed you today, that one can get even higher velocities, actually higher than 3 kilometers per second, and those can be achieved in ferrimagnetic insulators. And so they're achieved at angular momentum compensation temperature. All right, so with this, thank you for your attention.